I'd like to, so the videos I've been providing you on our e-learning days have been targeting square roots and radical equations. When we say radical equation, it doesn't have to be a square root. It could be a cube root, fourth root, fifth root. Predominantly, we work with square roots. We might see a couple cube roots. But I want to talk about how we solve these equations. So what we're seeing, or what we're going to see in some of the questions that were on the assignment that I gave you yesterday were, if you were to watch the videos that I asked you to watch on Friday, you should have been able to solve the equations that were in the assignment yesterday. But basically what I was asking is, if I have like radical x plus 1, let's go plus 2. Yeah, one of the ones that I posted that were e-learning should say something about the date. Like it should say, might say 2/16 on it or something like that, or. Yeah, that's the one aside for today. So we might have like something like square root of x plus 2, let's say, is equal to 1. Okay. We haven't talked too much about what a radical function looks like. Okay, but this square root function, basically the general shape of it can be found by just taking x values and seeing what y values we get. Okay. The one thing about a root function, you cannot take the square root of a negative number. Okay, because remember what square root is, it's a number that you multiply by itself 2 times to get what is underneath here. Okay, well, let's say that number is -6. There are no two numbers that I can multiply together or one number by itself twice to get a negative, because a negative times a negative would be a positive, right? And a positive times a positive would be a positive. There's no way to get a -6. So that means that when I choose x values, I need to choose x values that keep this number positive. Okay? So the first x value, positive or 0. The first x value I'm going to choose are actually the number that makes this 0. Okay? So what number would make this x plus 2 become 0? -2. So I'll plug -2 in. Right now, all I want to do is think about what the graph of radical x plus 2 looks like. Okay? I plug -2 in, and I get square root of 0 underneath here. Okay? Well, square root of 0 is 0. Because we're asking, what is the number that I multiply by itself 2 times to get 0? Well, 0 times 0 does that. Okay? So now let's think about another. Let's think about a number like, let's put -1 there. What if I plug -1 in? If I plug -1 in here for x, what do you get underneath the radical? You get 1, right? One number multiplied by itself twice will give me 1. Be 1, right? Okay. Let's try. Let's put 2 in there. If I put 2 in there, what do I get underneath the radical? 4. What number multiplied by itself 2 times will give me 4? 2. And let's do one more. Let's do 7. If I put 7 in here, that will give me 9 underneath, right? And then the square root of 9 would be 3. So if I graph this, what we end up with, so if I go 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. Okay. So at -2, 0, we get that point right there. At -1, 1, we get that point. 2, 2. Go all the way out to 7, up to 3. If I connect those, we get a curve that kind of looks like that. Okay? All of our square root curves are going to look like that. So I'll show you the parent function for the square root. It looks like that. Okay, now it continues, as far as I go to the right, it continues to rise. It just rises pretty slow. Does that make sense? Okay. Now, if I add or subtract, let's just say add a to this. Okay, so you can see that adding something underneath or subtracting something underneath will move that curve left and right. Does that make sense? Okay. If I put a number out in front, let's put B out front like this. When I change the B value, all it does is it makes it get taller faster. Is that okay, everybody? But all your root functions are going to look something like that. Okay. Now, when I solve an equation, so let's go back to the original equation that I had. I wanted x plus 2 equaling 1, or square root of x plus 2 equaling 1. If we forget how to solve equations, okay, by hand, using inverse operations and things like that, we can always solve them using graphs. Okay? So if I can graph the left-hand side of this equation, and that's what that looks like. That's exactly what we came up with here in red. Okay? And then I can graph the right-hand side of the equation separately. We get something like that. Does that make sense? Okay? Now, the solution to this equation then is the x value where these two things intersect. They intersect right there at point A, and the x value at point A is -1. So the solution that we should come up with here in a moment should be -1. Does that make sense? Okay. Now, what happens is as we go through these problems and we solve these problems, the first step that we go through, does anybody remember, if I wanted to solve this going off of what the video showed, let me change color here for a minute. Does anybody remember what I need to do? If I'm trying to solve this algebraically, what I need to do, I need to square both sides. So we use the inverse operation. So much like, if it was just x plus 2 equals 1, you would subtract 2 from both sides, right? Well, that's the inverse operation of the addition right here. Before I can do that, I need to get rid of the radical. So we use the inverse of the radical, which is to square things. Okay? So I'll square both sides, and it leaves me x plus 2 equals 1. Does that make sense? So now this is a new equation ultimately. Okay? So I want to graph what that looks like. X plus 2 being the left-hand side, and 1 being the right-hand side. Okay. Now, where these two, so we're looking at this white graph over here, where these two intersect is point B. Okay. And the x value would be -1. Does that make sense? Okay. So what I'm trying to get at here, as you go through and you start going through your order of operations and inverse operations to solve equations, okay, the next step here would be to subtract 2, right? You get x equals -1, right? Okay. So if I don't have a third graph here, but I could graph if I graphed x in -1, okay, something like that. Actually, sorry, it should be y equals -1. There we go. Y equals -1. So we're looking here. If we look at those two, where do those intersect? What is the x value where these two over here intersect? -1, right? So what I'm trying to show you is that each time that we go through a process in our equation to generate a new line of information, this new line of information right there is a different set of graphs than what we started with. Does that make sense? This here is a different set of graphs than what we started with. Okay. However, the solutions to what we started with, because that's what we're looking for, right? We're looking for those solutions. Those solutions exist in these others. Okay. And what that does for us, if we phrase it that way, that means all the solutions that when I'm done, okay, and I look at them, maybe I got 1 solution, 2 solutions, 3 solutions, however many I might have. Okay, within that group of solutions when I'm done are the solutions to the original problem. But it does not mean that every one of those when I'm done is a solution to the original problem. Okay, and the reason for that is the squaring process. When we go through, right, we're gonna get a process here that we have to go through every time that we square something. Okay, because that operation that creates what we call extraneous solutions. Okay. Okay. 2 words here. Extra. Okay. And then there's another. Have you ever heard the word erroneous? If somebody says something and like, I don't know, I say, Noah, that haircut is atrocious. And he says, that is erroneous, Faye. That is totally erroneous. What is he saying? That's false. That's wrong, right? Okay. So put those 2 words together, put extra and erroneous together, you get extraneous, which means it's an extra solution that is false for the original problem. Does that make sense? Okay. And when we square things, we always got to be on the lookout for that. Okay. So there's always going to be a last step here that we have to make sure that we pay attention to, because we might get an answer that really doesn't work. Okay. So when we, and all the things that I've taught you, I've always shown you a technique to check it, right? Okay. Do we always do that individually? No. Okay. I'd probably argue that many of us don't check much of the things that we do, right? Okay. Whether that be because we don't want to, or we are just that confident in our answers, you're right all the time. Okay. With solving radicals, you have to check your answers every time. Okay. Radical equation that has a variable in a radicand. Okay, so this is not, so if I had something like radical 2 and x out here equals like 5, even though there's a radical there, the variable is not underneath the radical, so that is not considered a radical equation. That is still a linear equation. Okay. The radical equation would look something like this. See how now the x is underneath the radical? That's part of, we call that the radicand. That creates a radical equation. Okay. Say it again? Yes. So what we did up here earlier, oh, down at the bottom? Yes. So all of these would be radical equations because the variable is underneath the root symbol, right? When we are talking about like all of these down here, because I don't put a number out in front, I don't put that index out in front of the radical, we're assuming they're square roots. So therefore, we will use the power of 2 as the inverse. If I can change the problem completely by putting a 3 out here. Because now instead of using the square root, we would use, or the power of 2, we would use the power of 3. Does that make sense? So everything that we do, I want to show you doing this stuff with square roots, but you can then extend that to cube roots, fourth roots, fifth roots, whatever you want to. Okay, it's the same exact procedure all the time. All right, so here are the steps. Okay, first thing you have to do is you have to isolate the radical. Okay, before you square things, you have to isolate the radical. Okay, if you do not do that, you're going to create a messier, more confusing problem. Okay, that you're just going to get deeper and deeper into radical work if you don't isolate the radical first. Okay, so that has to be done. So once the radical is isolated, use the inverse power to cancel the radical symbol. Okay, and all the rest of this says is if we have a different radical, like a cube root, fourth root, whatever, then we use the appropriate power to cancel. Okay. Once squaring is completed, okay, if the resulting equation is linear, which the largest x variable has a power of 1, solve for x. If the largest power is x squared, then you have to factor to solve for x. That is generally, I'm not going to say always, but that is generally part A here when you get extraneous solutions. Okay. Step 4 says whenever you square an equation, to rid yourself of a radical, you alter the graphing system that is behind the scenes. And because this alteration that happens, and I'll show you graphically tomorrow some situations where this happens, your graphs that you generate in the second, third, fourth steps may intersect more than what your initial one did. Therefore, your resulting answers might be in multitude, or the amount might be greater than what your initial equations intersections were. So we have to decipher that. We have to figure out which ones worked and which ones did not work. So those steps will hopefully get us there to start these examples tomorrow. I will, don't worry about that assignment, okay? I will extend that beyond whatever the due date is right now. 19th, okay. So no new homework this evening, okay? But come ready tomorrow. We're going to knock out these examples, and then hopefully have a little bit of time to work on your assignments. Jenna, you got a question?